The universe holds secret passageways written into its very fabric. These are wormholes, not science fiction fantasy, but serious predictions from Einstein's own equations of gravity. By the end of this exploration, you will understand the real science behind these cosmic tunnels, the staggering possibilities they unlock, and the monumental reasons we may never walk through one. We will confront the exotic matter that defies known physics and the time travel paradoxes that threaten reality itself. What would it mean if our universe was stitched together by these hidden threads? Einstein's revolution was a profound shift in perspective. He proposed that space and time are not a static stage where events simply play out. Instead, they are woven together into a single, dynamic entity called spacetime. Think of it not as a rigid grid, but as a flexible, four-dimensional fabric. This fabric is everywhere, the very canvas of our universe, and what gives this canvas its shape? Mass and energy. A planet, a star, any object with mass sits within this fabric and causes it to curve, much like a heavy bowling ball placed on a taut, stretchy sheet. That curvature, that dip in the fabric, is what we experience as gravity. The Earth orbits the Sun not because of some mysterious, invisible force pulling it, but because it is simply rolling along the curved geometry of spacetime created by the Sun's immense mass. This elegant idea, general relativity, completely reshaped our understanding of the cosmos. But if spacetime is a fabric that can be stretched and warped, then the geometry of that fabric allows for some truly bizarre possibilities. The equations of general relativity are like a set of instructions for how this cosmic cloth can be folded, pinched, or even stitched together in unconventional ways. Within this flexible framework, the mathematics does not forbid the existence of tunnels, shortcuts through the folded layers of the fabric itself. These theoretical passages are what we call wormholes, not because the math invents them, but because the math reveals they could be a natural, if extreme, feature of a universe where spacetime is dynamic and malleable. Before we can even begin to grasp these cosmic shortcuts, we must first fully appreciate the nature of the fabric they would be built from. It was within this landscape of warped geometry that the first real blueprint for a tunnel emerged. In 1935, Albert Einstein himself, working with his colleague Nathan Rosen, was exploring the mathematical description of a black hole. They found something astonishing hidden within the equations. The math did not just describe a one-way plunge into a point of infinite density, a singularity. Instead, it suggested that the fabric of spacetime, stretched to its absolute limit by the black hole's gravity, could potentially fold over and connect to another region entirely. They called this structure an Einstein-Rosen bridge. Picture not just a bottomless pit, but a tunnel, a literal bridge through the folded layers of the cosmos, linking two distant points. Initially, this bridge was seen as connecting a black hole, a point of ultimate gravitational pull, to its theoretical opposite, a white hole. A white hole would be a region of spacetime where nothing could ever enter, only expel matter and energy outward, like a cosmic fountain that cannot be approached. So this first wormhole was envisioned as a one-way street from a destructive collapse to a creative outburst. But there was a catastrophic problem. This bridge was unimaginably fragile. The moment it formed, the intense gravitational forces at its throat, the narrowest part of the tunnel, would cause it to pinch shut violently. The bridge would snap closed in an instant, far faster than even a beam of light could traverse it. This meant the Einstein-Rosen bridge was less a usable passage and more a fleeting ghost in the equations, a mathematical possibility that reality would instantly erase. It was a profound discovery, proving such structures could exist in theory, but it was also a dead end for anyone dreaming of interstellar travel. The universe, it seemed, had written the rules to keep its shortcuts sealed shut. For decades, the Einstein-Rosen bridge remained a beautiful mathematical phantom, a hint of cosmic architecture that reality itself seemed to forbid. Then, in 1988, physicists Michael Morris and Kip Thorne asked a radically different question. They did not start with a known object like a black hole and see where the math led. Instead, they began with a dream and worked backwards. What would it take, they wondered, to build a wormhole you could actually travel through? Their goal was to design a stable, traversable tunnel, a blueprint for a cosmic shortcut that would not instantly collapse. This flipped the entire investigation on its head. Rather than accepting the harsh rules of the universe as fixed, they asked what new rules would be necessary to bend them. They imagined the classic shape we recognize today, a throat, a smooth tunnel connecting two distant regions of space, often visualized as two funnels joined at their narrowest points. Picture the universe not as a flat sheet, but as a three-dimensional volume, like a vast block of clear gelatin. If you could pinch two distant points within that block and bring them together, the tunnel connecting those pinched regions would be the wormhole throat. Morris and Thorne meticulously outlined the engineering specs for such a passage. It had to be large enough for a traveler, its throat wide and smooth, free of deadly tidal forces that would stretch a human into a strand of atoms. Most crucially, it had to be held open against the relentless urge of gravity to crush it shut. This was the pivotal shift, moving the conversation from observing impossible cosmic curiosities to actively theorizing about engineered possibilities. Their work was not a discovery of a natural object, but the creation of a theoretical spec sheet, a recipe for a phenomenon the universe might not make on its own, but that the laws of physics perhaps do not entirely forbid. The real shock came when they calculated the ingredients required for this recipe. To prop open the throat of their wormhole, to prevent it from snapping closed, their equations demanded something truly bizarre, a substance with properties unlike anything we have ever seen. The recipe for a stable wormhole called for an ingredient that defies common sense. To prevent the tunnel from collapsing, the Morris-Thorne model revealed that its walls would need to be lined with something called exotic matter. This is not just a rare or unusual substance, it is a material that fundamentally inverts the rules of physics as we know them. Normal matter, everything from stars to dust to our own bodies, has positive energy density. It creates the attractive pull of gravity that curves spacetime inward. Exotic matter would need to do the opposite. It would have to possess negative energy density or exert negative pressure. Think of it as a kind of anti-gravity mortar, a repulsive force pushing outward against the crushing weight of the tunnel's own geometry, actively propping the throat open to allow safe passage. This requirement is the single greatest physical barrier to building a traversable wormhole because it violates what physicists call the classical energy conditions. These are bedrock assumptions that all known forms of matter and energy obey. They state, in essence, that gravity is always attractive and energy density is always positive. Exotic matter shatters these rules. We have never observed a macroscopic amount of it anywhere in the universe. Its existence is purely theoretical, a mathematical necessity for this particular cosmic architecture. There are, however, faint whispers from the quantum world that suggest such effects might not be entirely impossible. In the strange realm of quantum field theory, empty space is not truly empty. It seethes with virtual particles that flicker in and out of existence. Under certain extreme conditions, like between two incredibly close parallel metal plates in what is called the Casimir effect, these quantum fluctuations can create a tiny, measurable region of negative energy density. The plates are pushed together by the pressure of nothingness itself. This proves the concept exists in nature, but only on a vanishingly small scale. The amount of negative energy needed to stabilize a wormhole large enough for a person, let alone a spaceship, is astronomically larger. We are talking about the energy equivalent of converting an entire star, perhaps even a galaxy, into this bizarre, repulsive substance. So while the mathematics allows for the blueprint, the construction materials remain entirely out of reach, locked away in a speculative physics we do not yet understand. This potential for a stable tunnel transforms a cosmic curiosity into a profound promise. The core appeal of a traversable wormhole is its power to rewrite the map of the universe. It offers the ultimate shortcut. The distances between stars are so immense that light itself, the fastest thing we know, takes years to travel from our sun to its nearest neighbor. A journey to another galaxy with conventional propulsion is a fantasy spanning millions of human lifetimes, but a wormhole changes the geometry of the problem entirely. A classic analogy is to think of the universe as a vast sheet of paper. 2 points on opposite ends of that sheet might be separated by a long, arduous journey across its entire surface. But if you fold the paper, bringing those 2 distant points to touch each other, you create a direct connection, poke a hole through where they meet, and you have a tunnel, a wormhole, that bypasses the entire journey across the surface. The traveler does not move faster than light across the expanse. They simply take a different, shorter path through the folded layers of spacetime itself. A trip that should take 100,000 light-years could, in theory, become a journey of mere minutes through the throat of the tunnel. The implications of such a structure are staggering. It would not just be a new engine, it would be a new kind of door. Instantaneous travel between unimaginably distant star systems becomes conceivable. Communication across the cosmos would no longer suffer the agonizing delays of light speed. A message sent through a wormhole could arrive in another galaxy at the same moment it was sent, making true interstellar conversation possible. But the deepest implication is for the universe's own architecture. If such tunnels exist, our cosmos is not simply a vast, empty volume where every point is separated by a direct, unobstructed line. Instead, it could be multiply connected, a cosmic labyrinth where 2 locations that appear impossibly far apart in ordinary space are secretly neighbors through a hidden passage. This suggests a universe that is intricately woven together in ways we cannot see from our limited perspective, a reality stitched with invisible threads that bind its most distant realms. It is this breathtaking vision, the dream of a connected, navigable cosmos, that provides the profound motivation to keep wrestling with the daunting physics. The promise is so transformative that it compels us to ask if the universe, in its deepest laws, might allow such a thing after all. But the Morris-Thorne model is just one architectural style in a universe of theoretical possibilities. Physicists have explored several distinct families of wormholes, each born from a different set of mathematical assumptions and cosmic contexts. The first and most famous type is the Lorentzian traversable wormhole, the very design we have been discussing. This is the classic tunnel through spacetime, a shortcut that a traveler could, in principle, pass through in real time. It exists within the familiar 4-dimensional fabric of our universe, the realm where cause and effect flow forward. The Morris-Thorne blueprint falls into this category, a structure that could connect 2 distant beaches on the same cosmic shore, if only we could find the exotic mortar to build it. Then there are Euclidean wormholes, which operate in a completely different conceptual landscape. These are not tunnels you could ever fly a ship through. Instead, they are conceptual bridges within the quantum foam, the seething, probabilistic foundation of spacetime at the smallest possible scales. In this realm, the sharp distinction between space and time blurs, and the geometry of the universe can fluctuate wildly. A Euclidean wormhole represents a fleeting, ghostly connection that might briefly stitch together different points in this quantum foam before dissolving away. They are less like cosmic highways and more like ephemeral threads in the fabric's underlying weave, significant for theories of quantum gravity, but not for interstellar travel. Their importance lies in the question of whether our universe's very spacetime might have been born from such a quantum connection. Perhaps the most mind-bending category is the inter-universe wormhole. This idea stretches the concept to its absolute limit, proposing a tunnel that does not connect two points within our cosmos, but bridges between two entirely separate universes. This speculation arises from multiverse theories, where our universe is just one bubble in a vast cosmic froth of expanding realities, each with its own distinct laws of physics. An inter-universe wormhole would be a cosmic umbilical cord, a hypothetical link between these isolated bubbles. Traveling through one would not just move you across space, but would literally exit one reality and enter another, a journey into a completely different cosmic story with potentially alien physical laws. While this remains the most speculative of all, it demonstrates how the simple idea of a tunnel in space-time can expand to encompass the grandest visions of reality's structure, from the quantum foundations of our own world to the possibility of an infinite multiverse beyond it. The dream of a cosmic shortcut carries a hidden and deeply troubling consequence. To understand it, we must revisit a core principle of Einstein's universe, the fact that time itself is woven into the fabric of spacetime and is not absolute. Time flows at different rates depending on gravity and motion. A clock on a fast-moving spaceship ticks slower than one on Earth, an effect called time dilation. Now apply this to our wormhole. Imagine we have a stable Morris-Thorne tunnel with two mouths, mouth A and mouth B. They are synchronized, so stepping into A and out of B is an instantaneous trip across space with no difference in time. But what if we take one of those mouths, say mouth B, and put it on a spaceship? We send that ship on a long journey at a significant fraction of light speed, experiencing intense time dilation, and then bring it back to rest near mouth A. From the perspective of the moving ship, time passed more slowly, so when mouth B returns, less time has passed for it than for the stationary mouth A. The two ends of the same tunnel are now out of sync. Mouth B might be, from our perspective, 5 years in the past relative to mouth A. This is where the geometry becomes a time machine. If you now step into the stationary mouth A, you exit from the traveled mouth B, but you emerge at the location and moment in time when that mouth returned, which is 5 years in the past relative to when you entered. You have not just traveled through space, you have traveled backward in time. You could then walk a short distance through normal space to the stationary mouth A, which exists in that past moment, step into it, and emerge from the traveled mouth B at an even earlier point. In theory, this creates a closed time-like curve, a path through spacetime that loops back on itself, allowing for travel into one's own past. The implications of this are not just strange, they are fundamentally disruptive to our understanding of reality. The most famous thought experiment is the grandfather paradox. Imagine using such a wormhole time machine to go back to a time before your grandfather met your grandmother. If you were to prevent that meeting, you would ensure your own birth never happened. But if you were never born, you could not have gone back in time to interfere, which means the meeting would happen, and you would be born, creating a logical loop with no consistent outcome. This paradox suggests that time travel to the past, as commonly imagined, introduces impossible contradictions that the laws of physics seem designed to prevent. To address this, some physicists, like Igor Novikov, proposed a guiding principle. The Novikov self-consistency principle asserts that if time travel to the past is possible, then the laws of physics must conspire to make events consistent. You could go back in time, but you would find yourself utterly unable to change any event that you know already happened. Your actions in the past would inevitably, through coincidence or subtle physical constraints, lead to the exact present you left from. In this view, history is a single, immutable story, and time travelers are merely actors playing out a role they were always destined to play, their free will an illusion within the loop. This principle is one way to rescue causality from paradox, but it paints a universe where the past is locked, a fixed tapestry where every thread, including those woven by time travelers, was always part of the pattern. The paradox of time travel forces us to confront the very nature of causality. But what if wormholes are not just cosmic anomalies, but woven into the fundamental fabric of existence? To find an answer, we must shrink our perspective from the vastness of galaxies down to the smallest conceivable scales, to a realm where the rules of general relativity and quantum mechanics collide. This is the domain of quantum gravity, and here, the concept of the wormhole transforms once more. At the unimaginably tiny scale of the Planck length, a distance so small it has almost no meaning in our everyday world, the smooth, warped fabric of spacetime described by Einstein ceases to exist. Instead, it is theorized to become a chaotic, frothing sea known as quantum foam. In this seething foundation of reality, the concepts of space and time themselves lose their definite meaning. Energy fluctuations at the quantum level are so violent that they cause the geometry of spacetime to twist, pinch, and fluctuate wildly. It is within this probabilistic frenzy that the most primordial form of wormhole is imagined to exist. Here, at the absolute bedrock of physics, microscopic wormholes are thought to blink in and out of existence constantly, like bubbles forming and popping in a boiling pot. These are not tunnels one could ever traverse. They are ephemeral structures far smaller than an atom, lasting for mere fractions of a second. They represent a potential, fundamental texture of reality, a foam whose very bubbles might be interconnected by these fleeting bridges. This vision suggests that the connectivity offered by wormholes is not a rare or engineered feature, but a basic property of spacetime at its most fundamental level. The smooth cosmic landscape we perceive is merely an average, a calm surface over a deep and turbulent quantum ocean where connectivity is the rule, not the exception. It hints that the universe may be inherently connected from the very beginning, with every point in space subtly linked to every other through a labyrinth of transient, submicroscopic threads. This bridges our grand, macroscopic theories with the cutting edge of quantum physics, proposing that the hidden passages we dream of navigating between stars might simply be amplified, stabilized versions of a connectivity that is happening everywhere all the time in the quantum shadows beneath our feet. This quantum foam of potential connections leads to an inevitable question for astronomers. If these cosmic tunnels are woven into reality's fabric, even on a grand scale, could we ever hope to see one? The search moves from the blackboard to the telescope, shifting from pure theory to the challenging art of observational astronomy. Since a wormhole would not emit light itself, we must look for its ghostly signature, the subtle ways it would warp the space and light around it. Our primary tool for this hunt is gravitational lensing, the same phenomenon that proves massive objects bend the path of light. We use it to study black holes and dark matter, but a wormhole's lensing effect could be uniquely strange. A black hole with its event horizon creates a characteristic shadow, a dark disk ringed by a bright halo of distorted light. A traversable wormhole with its open throat and lack of an event horizon might create a different kind of phantom in the data. Instead of a single warped image or a dark shadow, light passing around a wormhole could produce a double image, or even a distinctive, bright ring with a central bright spot, like a cosmic donut with a glowing hole. The geometry of the tunnel could act as a bizarre lens, bending light from objects behind it in ways no single massive object could replicate. Astronomers would scour the data from telescopes, looking for these gravitational anomalies that stubbornly refuse to match the models for black holes or neutron stars. Beyond lensing, there are more speculative signatures. If a wormhole's throat is lined with the exotic matter needed to hold it open, that matter might radiate in peculiar ways. We might search for unexplained bursts of energy or patterns of radiation that defy known sources. Perhaps the mouth of a wormhole would exhibit strange quantum vacuum effects, a detectable shimmer in the fabric of spacetime itself. The challenge is monumental. Any candidate would be extraordinarily difficult to distinguish from other exotic compact objects. An unusual lensing pattern could be caused by a complex cluster of dark matter or a rapidly spinning black hole with a peculiar accretion disk. What looks like exotic radiation might be a previously unknown type of stellar explosion. At these immense distances, we are interpreting faint whispers from the dark. To date, no confirmed detection of a wormhole exists. Every potential signal has a more conventional, if still mysterious, explanation. This search is perhaps the ultimate test of our scientific imagination, training our most advanced instruments to find not just new objects, but a new kind of geometry hidden within the old. The hunt for these cosmic tunnels hinges on catching their ghostly fingerprint in the data. Among all the detection methods, gravitational microlensing offers one of the most promising and elegant ways to listen for their whisper. This technique relies on a simple, beautiful principle of Einstein's universe. When a massive object passes almost directly between a distant star and our telescopes here on Earth, its gravitational field acts as a natural lens. It bends and focuses the light from that background star, causing it to temporarily brighten in a predictable pattern. Astronomers have used this method for years to detect everything from rogue planets to faint stellar remnants. But a wormhole would not play by the same rules. Its spacetime geometry is fundamentally different from a simple, dense lump of matter. Imagine the light from a distant star approaching the mouth of a traversable wormhole. Instead of being bent by a single, concentrated gravitational well, the light would encounter the bizarre, double-throated structure of the tunnel. As the wormhole passes between us and the star, the light would be distorted in a uniquely symmetrical way. The resulting brightening of the star, what scientists call a light curve, would rise to a peak and then fall away in a pattern that is a near-perfect mirror image. This time-symmetric signature is the theoretical smoking gun. A single massive object like a black hole or a dim star creates an asymmetric light curve. The brightening and fading are not perfect mirrors because the lensing effect is not identical on the approach and the departure. The wormhole's distinctive double-mouthed geometry, however, could theoretically produce that clean, mirrored signal. It is a subtle but crucial difference written in light. To catch such an event, astronomers must engage in a cosmic watch on an epic scale. Projects like the Optical Gravitational Lensing Experiment, or OGLE, and others continuously monitor hundreds of millions of stars in dense fields, like those toward the center of our galaxy. They are automated sentinels collecting mountains of data night after night, searching for the telltale flickers that betray unseen masses drifting through the interstellar dark. The odds of a wormhole alignment are vanishingly small, but by watching so many stars for so long, the surveys create a statistical net. In principle, if a stable wormhole of the right mass and size were to pass in front of a monitored star, its symmetric light curve would stand out as a profound anomaly in the data. It would be a single, exquisite data point screaming that something with a geometry unlike anything else we know is out there. The search is a testament to patience and precision, sifting the cosmic noise for a signature that may not exist, but if found, would forever change our map of reality. Gravitational lensing searches for a ghost, but what if the ghost was never born naturally? The profound question we must confront is whether the universe itself could ever sculpt a stable, traversable wormhole through its own processes, or if such a structure would forever remain a monument to intelligence. The early cosmos was a cauldron of unimaginable energy, where spacetime itself was malleable and wild. Some theories speculate that microscopic wormholes, those quantum foam bubbles, could have been stretched to macroscopic sizes during the period of hyper-fast expansion known as cosmic inflation. In this view, the rapid stretching of the fabric of reality might have taken a fleeting quantum connection and inflated it like a cosmic balloon, potentially leaving behind a network of primordial tunnels woven into the large-scale structure of the cosmos. Other speculative ideas involve cosmic strings, hypothetical one-dimensional defects in spacetime left over from the early universe. If two such strings crossed, their immense gravitational fields might theoretically warp spacetime into a tunnel-like configuration. There is also the exotic concept of quantum tunneling applied not to particles, but to spacetime geometry itself, where the universe could spontaneously transition into a state containing a wormhole. These are fascinating possibilities pushing the boundaries of cosmology and quantum gravity. Yet, for all their theoretical intrigue, they face a monumental hurdle: stability. A wormhole born from these chaotic processes would almost certainly be a chaotic object itself, prone to instant collapse or riddled with lethal radiation. It would be a cosmic accident, not a cosmic highway. The overwhelming consensus in physics is that a wormhole useful for travel, one that is macroscopic, stable, and safe for passage, would not arise from natural astrophysical processes. The requirements are simply too precise, too fine-tuned. The need for exotic matter in vast quantities, arranged in a specific configuration to hold the throat open against gravitational collapse, points away from a natural origin. It points toward design. This leads to a staggering implication. If we were ever to detect a genuine traversable wormhole, the most plausible explanation might not be that we found a strange quirk of nature, but that we found an artifact. It would be evidence of engineering on a scale that bends the universe to its will, a construction project of a civilization so advanced that their technology appears to us as natural law. Such a discovery would transform the wormhole from a theoretical curiosity into the ultimate signpost, a beacon in the darkness, not merely saying that connection is possible, but that someone, somewhere, has already built the bridge. Building a bridge across the stars is one thing, but keeping the tunnel from collapsing is an engineering nightmare of cosmic proportions. The exotic matter is not simply a magical ingredient you sprinkle into the structure. It must be arranged with impossible precision. Imagine trying to line the entire interior surface of a tunnel, one that might be millions of kilometers long, with a substance that actively pushes against the universe's desire to crush it shut. This lining cannot have a single weak point, not one microscopic flaw in its distribution. The gravitational forces at the throat are so immense that any irregularity, any thinning of this exotic mortar, would trigger an instantaneous, catastrophic collapse. The entire structure exists in a state of perfect, violent tension, a balance between the crushing weight of curved spacetime and the repulsive push of the exotic matter holding it at bay. It is less like building an arch and more like trying to inflate a balloon inside a hydraulic press, where you must maintain exactly the right internal pressure at every single point forever against an external force that never relents. The scale of this task defies comprehension. To stabilize a wormhole even 1 meter wide, some calculations suggest you would need a concentration of negative energy equivalent to converting the mass of Jupiter into this bizarre substance. And that is just for a microscopic passage, not a star gate. For a tunnel large enough for a ship, the required mass energy could rival that of an entire galaxy. We are not talking about mining an asteroid. We are talking about alchemizing the collective output of 100 billion stars into a form of matter that may not even be possible to assemble in bulk. This moves the challenge far beyond mere material science. It implies that constructing a traversable wormhole is not just an engineering problem, but an act of fundamental physics manipulation. It would require not just finding exotic matter, but learning to sculpt the underlying geometry of spacetime itself, to command gravity and quantum fields with a precision that looks, from our current vantage point, indistinguishable from magic. The blueprint exists in the equations, but the tools to build it belong to a civilization that has learned to write its own laws onto the fabric of reality. The very geometry that creates a cosmic shortcut also hides a deadly trap, one that defines the most famous cosmic objects of all. This is the event horizon, the point of no return around a black hole. It is not a physical surface, but a mathematical boundary in spacetime, a one-way membrane from which not even light can escape. For a wormhole to be traversable, to be a passage and not a prison, its throat must be completely free of such a horizon. The moment an event horizon forms within the tunnel, the shortcut becomes a dead end. Anything entering would be inexorably pulled toward the singularity at its core, stretched and crushed in a process physicists call spaghettification, with no possibility of ever reaching the other side. The Morris-Thorne model is carefully designed to avoid this fate. Its blueprint specifies a throat that is smooth and horizon-free, a tunnel you could theoretically enter and exit without encountering that ultimate point of no return. This is achieved through the precise application of that exotic matter, which provides the outward pressure to keep the throat open and stable, preventing the gravitational collapse that would naturally form a horizon. But this introduces a terrifying fragility. The balance is unimaginably delicate. Any perturbation, any slight imperfection in the distribution of the exotic matter lining the tunnel, any external influence like a stray asteroid or even a burst of radiation passing through could theoretically upset this perfect equilibrium. If the balance tips even slightly, the repulsive force might falter for a fraction of a second. In that instant, the relentless force of gravity could take over, causing the throat to pinch just enough to form a temporary, microscopic event horizon. For a traveler inside at that exact moment, the consequences would be absolute and immediate. Their journey through the stars would end not at a new world, but at the crushing end of spacetime itself. This means maintaining a traversable wormhole is not a one-time construction project. It is an act of perpetual, vigilant control. It requires constant monitoring and active stabilization, a dynamic process of adjusting the exotic matter to counteract any and all disturbances in real time. The tunnel is not a static piece of cosmic infrastructure. It is a living, breathing entity held in a state of forced calm against a universe that constantly tries to turn it into a tomb. This adds a profound new layer of risk and complexity to the theoretical construct. It suggests that even if we somehow acquired the impossible materials to build such a bridge, we would also need the godlike control to keep it safe, ensuring that the doorway to the stars never silently transforms into a door that only swings one way into an endless dark. The delicate balance needed to prevent a horizon hides another, more insidious danger. Even if the throat of a wormhole remains open, the sheer curvature of spacetime there could be lethal on its own. This threat comes from tidal forces, the difference in gravitational pull from one end of an object to the other. You experience a mild version of this right now. The Moon's gravity pulls slightly harder on the side of the Earth facing it, and slightly weaker on the far side. This difference stretches our oceans, creating the tides. Now amplify this effect by a factor of billions. Near a region of extreme spacetime curvature, like a black hole or the narrow throat of a wormhole, that difference becomes catastrophic. The pull on your feet would be unimaginably stronger than the pull on your head. Your body or a spacecraft would be stretched into a long, thin strand, a process physicists vividly term spaghettification. It is not a slow pull, but a violent, instantaneous transformation. For a black hole, this happens well before you cross the event horizon, a final, gruesome farewell from the universe. For a traversable wormhole, this presents a fundamental engineering constraint. The very geometry that creates the shortcut also creates these monstrous tidal gradients. A tunnel is useless if anything passing through it is shredded into atoms. Therefore, a truly traversable model must not only be held open, it must be made incredibly smooth and gentle. The curvature at its narrowest point cannot be too sharp. The throat must be wide enough and the transition through it gradual enough that the difference in gravity from the front to the back of a spacecraft remains within survivable limits. This imposes another layer of precise, demanding specifications on the wormhole's design. The exotic matter lining the tunnel must not just provide repulsive pressure, it must also be configured to shape the gravitational field in a very specific, forgiving way. It is not enough to build a door, you must build a doorway with a gentle, welcoming ramp, ensuring the passage itself does not become a destructive force. This further shrinks the window of possibility, demanding a level of control over spacetime geometry that seems to border on the miraculous. The universe's shortcuts, it seems, are protected by guardians of sheer physical violence, challenges that must be solved not just in theory, but in the brutal, practical reality of keeping a traveler intact. Beyond the crushing forces of gravity lies a far more subtle and insidious threat. To understand it, we must venture into the strange intersection where the vast geometry of spacetime meets the frantic dance of the quantum world. This is the realm of quantum field theory in curved space, and it suggests that the very act of bending the universe into a tunnel could awaken a sleeping dragon. Within the violently warped region of a wormhole throat, the fabric of reality is stretched and contorted to an extreme degree. According to our best theories, empty space is not truly empty. Even in the darkest vacuum, the quantum fields that underpin reality are constantly fluctuating. Tiny pairs of virtual particles and antiparticles flicker into existence and then annihilate each other almost instantly. This is the quantum foam, normally a quiet background hum, but place these fields in a severely curved geometry, like the steep slopes of a wormhole throat, and that quiet hum can become a deafening roar. The intense gravitational gradients can rip these virtual particle pairs apart before they can destroy each other. One particle gets sucked into the negative energy state of the exotic matter, while its partner is ejected as real, high-energy radiation. This process is conceptually similar to Hawking radiation, the faint glow theorized to emanate from black holes. But in the context of a wormhole, the effect could be catastrophic, not a faint whisper but a torrent. The throat of the tunnel could become a natural particle accelerator, flooding the interior with an intense flux of gamma rays and other high-energy particles. For any traveler, this would not be a gentle light show. It would be an unsurvivable bath of radiation, sterilizing the passage in an instant, and the danger is not just to the traveler. This burst of quantum activity, this conversion of virtual particles into real energy, could fundamentally destabilize the delicate balance holding the wormhole open. The radiation carries energy, and energy curves spacetime. This additional chaotic curvature could act as a wild perturbation, disrupting the precise arrangement of exotic matter and triggering the very collapse the structure was designed to prevent. So here lies a profound quantum mechanical hurdle. Even if we somehow solved every classical problem, mastering exotic matter and taming tidal forces, the universe might still defend its secrets with a quantum trap. The act of creating a shortcut could inadvertently create a furnace, a byproduct of spacetime's own resistance to being bent into such an unnatural shape. This suggests that a truly traversable wormhole may require more than just bending gravity. It may demand a complete theory of quantum gravity, a way to calm the quantum fields themselves, to convince the universe's most fundamental ingredients that this drastic shortcut is a peaceful path, not a violent rupture in their domain. This quantum furnace within a wormhole's throat points to a deep conflict between the large and the small, between gravity and quantum law. Yet this very tension might also hint at a hidden unity, a connection to the largest mystery in all of modern cosmology. That mystery is dark energy. We know our universe is not just expanding, but its expansion is accelerating, as if some invisible, repulsive force is stretching the very fabric of spacetime apart. The source of this cosmic push is what we call dark energy. It constitutes about 70% of all the energy in the cosmos, and we have almost no idea what it is. The leading candidate is something known as the cosmological constant, a form of energy inherent to empty space itself that exerts a constant negative pressure. And here is where a speculative, breathtaking bridge can be built to our wormholes. The exotic matter required to hold a wormhole open is defined by its negative energy density and negative pressure, a substance that pushes outward against gravitational collapse. Dark energy, as described by the cosmological constant, is also characterized by a persistent, smooth negative pressure that drives the universe apart. While their scales and manifestations are wildly different, they share a profound conceptual kinship. They are both forms of energy that make gravity act in reverse, creating a repulsive effect. This has led some theorists to wonder if these two enigmatic phenomena, one governing the fate of the entire cosmos and the other enabling theoretical shortcuts within it, could be different faces of the same underlying physics. Perhaps the exotic matter needed to engineer a wormhole is not some rare, impossible substance, but a localized, concentrated form of the same dark energy that fills the universe. Imagine if we could learn to bottle the cosmological constant, to shape and focus the ambient repulsion that exists in every cubic centimeter of so-called empty space. In this speculative vision, building a wormhole would not be about inventing a new kind of physics from scratch, but about learning to sculpt a force that is already everywhere, weaving the universe's own expansive tendency into a stable, traversable arch. This idea is without question highly conjectural. The negative pressure of dark energy is incredibly weak, far too diffuse to hold open a macroscopic tunnel. It is like comparing the gentle push of a light breeze to the focused thrust of a rocket engine. Yet the mathematical similarity is provocative. It suggests that wormholes are not just isolated oddities in the theory of gravity, but may be intimately connected to the deepest questions about the structure and evolution of the cosmos itself. The same repulsive quality that determines the ultimate fate of all galaxies might, in a different configuration, be the key to connecting them. This positions the wormhole not as a mere engineering puzzle, but as a potential clue within a much grander puzzle. Understanding dark energy is the paramount challenge of 21st century cosmology. If its nature is ever unraveled, it might not just tell us how the universe will end, but could also reveal whether the universe's own expansive heartbeat could one day be harnessed to stitch its distant edges together. The search for a unified theory of reality may require us to step outside our familiar dimensions entirely. String theory, one of the leading candidates for a theory of quantum gravity, proposes that the fundamental ingredients of the universe are not point-like particles, but incredibly tiny, vibrating strings. To make the mathematics of these vibrations consistent, string theory demands a startling feature: the existence of extra spatial dimensions beyond the three we experience. Our entire universe, with all its stars and galaxies, could be a three-dimensional membrane or brain, floating within a higher dimensional expanse often called the bulk. This radical reimagining of cosmic architecture completely transforms the wormhole concept. A shortcut between two distant stars in our brain might not be the shortest path available. If a tunnel could momentarily leave our three-dimensional membrane and pass through the higher dimensional bulk, it could take a more direct route, like a worm burrowing through the soil instead of walking all the way around the hill on the surface. In this view, a wormhole is not merely a fold within our familiar space. It is a bridge that uses the added geometry of hidden dimensions to achieve an even more profound shortcut. The distances through the bulk could be vastly smaller than the corresponding distances constrained to our brain, making interstellar travel not just possible, but perhaps even trivial for a civilization that mastered bulk navigation. This speculative vision turns the cosmos into a labyrinth with secret passages accessible only to those who understand its full, multidimensional shape. Perhaps the most profound twist in this story connects the vastness of spacetime geometry to the spooky connections of the quantum world. In recent years, a startling theoretical conjecture has emerged, linking wormholes to quantum entanglement. It is summarized by a deceptively simple equation, ER equals EPR. On one side, ER stands for Einstein and Rosen, the pioneers of the Einstein-Rosen bridge. On the other, EPR stands for Einstein, Podolsky, and Rosen, who famously critiqued the bizarre implications of quantum entanglement. This equation proposes a deep and unexpected duality, that two quantum-entangled particles, which can instantaneously affect each other's state across any distance, might be secretly connected by a microscopic wormhole. The entanglement, that spooky action at a distance that so troubled Einstein, may not be a mysterious force, but a geometric connection, a tiny thread of spacetime stitching the particles together through the extra-dimensional bulk. In this radical picture, every entangled pair in the universe is joined by an unfathomably small Einstein-Rosen bridge. While these quantum wormholes are not traversable in any conventional sense, they suggest that the fabric of spacetime and the web of quantum information are not separate things, but two different descriptions of the same underlying reality. Space itself may be woven from a network of quantum entanglements, with classical geometry emerging from these countless microscopic connections. This idea bridges the greatest chasm in modern physics, hinting that the warped tunnels of general relativity and the invisible links of quantum mechanics are two sides of a single, deeper coin, a universe where information and geometry are fundamentally inseparable. This deep connection between entanglement and geometry leads us to a modern crisis in physics, one where the humble wormhole plays a starring role. It is known as the black hole information paradox, and it threatens the very logical foundation of quantum theory. The problem begins with Stephen Hawking's great insight that black holes are not truly black. They slowly evaporate, emitting a faint glow of radiation now named after him. Hawking radiation is purely thermal, a form of heat noise. It carries no specific information about the individual atoms, particles, or books that might have fallen into the black hole. According to Hawking's original calculation, when the black hole finally evaporates completely, all that intricate information about what formed it and what it consumed is lost forever, erased from the universe. This presents a catastrophic conflict. Quantum mechanics is built on the principle of unitarity, which states that information is never destroyed. It can be scrambled, hidden, or transformed, but it must always, in principle, be recoverable. If a black hole permanently deletes information, then quantum mechanics, our most successful theory of the small, is fundamentally wrong when it meets gravity. For decades, this paradox stood as an impasse. Then, a radical possible solution emerged, and it hinged on reimagining the Einstein-Rosen bridge. Perhaps, physicists suggested, the information is not lost at all. What if the interior of the black hole, the point beyond the event horizon, is not a dead end, but is secretly connected via a microscopic wormhole to the Hawking radiation streaming away into space? In this view, the radiation is not random thermal noise. It is subtly encoded with the information of everything that fell in, entangled with the interior through a vast, complex web of these quantum bridges. The information never leaves the black hole in a conventional sense. It is teleported via these space-time threads into the outgoing radiation. The black hole's evaporation is then not a deletion, but a transformation, a translation of matter into an intricate hologram of information spread across the radiation field. This elegant idea, however, spawned a new and equally fierce paradox of its own. If the Hawking radiation particles are perfectly entangled with the interior of the black hole, then, by the rules of quantum mechanics, they cannot also be entangled with each other. A principle called monogamy of entanglement forbids a particle from being fully entangled with two different systems. Yet, for an observer falling into the black hole, calculations suggested the space just inside the event horizon should be empty and peaceful, a vacuum following the laws of quantum field theory. In this empty vacuum, particles would be entangled with their partners on the other side of the horizon. So which is it? Is the radiation entangled with the interior, preserving information? Or is the vacuum just inside the horizon entangled across it, ensuring a smooth passage? You cannot have both. In 2012, a group of physicists argued this inconsistency meant the event horizon could not be a calm place. Instead, it must be a blazing wall of high-energy particles, a quantum firewall that would incinerate any traveler the moment they crossed. This firewall paradox forced the physics community to choose between three deeply held beliefs: that information is preserved, that quantum field theory holds near the horizon, and that an observer encounters nothing special when falling in. At least one had to be wrong. The ongoing struggle to resolve this crisis is where wormhole geometry has become absolutely central. The leading framework for a solution, known as holographic entanglement, uses the mathematics of wormholes, or more precisely, their higher dimensional representations, to show how information can be both inside and encoded in the radiation without a firewall. It proposes that the entanglement between the black hole interior and the Hawking radiation actually changes the geometry of spacetime itself, creating those microscopic wormhole connections that make the interior and the radiation one and the same system from a quantum perspective. This means the humble wormhole is no longer just a speculative tunnel for travel. It has become an essential tool in the most cutting-edge debate about the nature of reality, a key player in the quest to forge a theory of quantum gravity. The fate of information in the cosmos, and perhaps the final reconciliation of Einstein's gravity with quantum law, may be written in the language of these hidden bridges. Science fiction has always been the first frontier for cosmic ideas, and wormholes have become its most iconic gateway. From the solemn, machinery-filled vortex in Contact to the shimmering, water-like portal of Stargate and the breathtaking cosmic whirlpool of Interstellar, these tunnels have been visualized as humanity's ultimate elevator to the stars. These stories perform an invaluable service, translating complex equations into visceral wonder. They introduce millions to the mind-bending idea that space can be folded, that distance is not an absolute barrier. In doing so, they embed the theoretical possibility of wormholes deep within our cultural imagination, making the strange mathematics of relativity feel tangible and thrilling. Yet, this narrative power comes with necessary creative license. The films almost always gloss over the monumental challenges of stability and exotic matter. The wormhole is simply there, a fixed piece of cosmic infrastructure. Its terrifying fragility and impossible engineering requirements neatly sidestep to serve the story. A ship approaches, enters, and emerges, with no discussion of quantum radiation baths or the constant dynamic stabilization needed to prevent a collapse into a black hole. The exotic matter is an unseen given, not a universe-defying substance we must somehow conjure. This narrative shorthand is perfectly understandable. It allows the plot to focus on discovery and drama rather than a physics lecture. However, it creates a potent illusion of accessibility. The cinematic wormhole feels like a daunting but achievable technology, a natural next step in our evolution, rather than what it truly represents, a hypothetical monument at the very edge of known physical law, if not far beyond it. This contrast between the silver screen and the chalkboard is not a criticism of storytelling, but a crucial calibration of expectation. It highlights the vast gulf between a compelling plot device and a physical possibility. Science fiction opens the door to the question, what if? But it is real science that must wrestle with the infinitely more difficult how, and more fundamentally, whether the universe even permits such a door to be built at all. The cultural legacy of these stories ensures we look up at the night sky and wonder about hidden connections, but the equations remind us that some bridges might exist only in the architecture of our dreams. The profound silence of the cosmos presents a haunting question. Given the vast number of stars and planets, why do we see no signs of other advanced civilizations? This is the Fermi paradox, the stark contradiction between the high probability of alien life and the complete absence of evidence for it. One unsettling solution is the concept of a great filter, a developmental barrier so extreme that almost no civilization survives it. Perhaps the filter is not behind us in the rare miracle of life's origin. Perhaps it lies ahead, waiting for any society that reaches a certain technological zenith. And what could that ultimate civilization-ending test be? Wormhole engineering presents a terrifying candidate. The quest to build a stable cosmic shortcut might not just be difficult, it could be universally fatal. The very process of manipulating spacetime with such violent precision could unleash unintended consequences that erase the builders from existence. Imagine a civilization finally mastering the energy of stars, solving the riddles of exotic matter, and beginning the monumental task of stitching a tunnel through reality. In their moment of triumph, as they apply the final threads of negative energy to stabilize the throat, they might inadvertently trip a cosmic wire. The most speculative and dire risk is something physicists call vacuum decay. Our universe may exist in a stable, but not perfectly stable, state of empty space. The violent, concentrated energies involved in wormhole construction could, in theory, create a bubble of a more stable, lower-energy vacuum. This bubble would then expand at the speed of light in all directions, rewriting the fundamental laws of physics as it goes. Atoms would cease to hold together, chemistry would become impossible, and the very fabric of reality would be transformed into something unrecognizable. The civilization and everything in its region of spacetime would simply cease to be in any form we could understand. Alternatively, the act of stabilizing a traversable wormhole inherently risks creating closed timelike curves, those loops back into the past. The universe's laws may have a zero-tolerance policy for such paradoxes. Rather than allow a causality violation, the local geometry of spacetime could become so pathological and unstable that it simply breaks down, collapsing into a singularity or dissolving into chaos. The bridge to the stars becomes a detonator. In this grim speculative scenario, the great silence we observe is not because civilizations fail to reach for the stars, but because they succeed too well. Every brilliant star-faring culture, upon reaching the threshold of wormhole creation, inadvertently triggers its own end, vanishing in a flash of rewritten physics before it can ever signal its neighbors. The cosmos would be littered with the silent, invisible graves of those who touched the deepest architecture of reality and found it was rigged to collapse. This frames the wormhole not as a gateway, but as the universe's ultimate test, a filter so absolute that crossing it may be the last thing any civilization ever does. Stephen Hawking saw a universe that seemed to guard its own history. He called this the Chronology protection conjecture, a formal proposal that the laws of physics contain a built-in safety mechanism. Hawking reasoned that if time travel to the past were ever possible, even in theory, we should see tourists from the future. Historians would be tripping over time travelers at every major event. Since we see no evidence of visitors from tomorrow, he argued, something in the fundamental rules must actively prevent it. The conjecture suggests that whenever conditions arise that could create a closed timelike curve, a loop back into the past, quantum effects will always intervene to stop it. Think of it as the universe's immune system. Just as your body mobilizes defenses against an infection, space-time itself might react violently to the paradox of backward time travel, producing effects that destroy the very structure attempting to create it. In the context of a wormhole time machine, this protective mechanism could manifest in a dramatic and definitive way. As the two mouths of the wormhole are manipulated to create a time difference, the vacuum of empty space around the tunnel would not remain calm. According to quantum field theory, the increasing distortion would cause virtual particles to become real in a runaway feedback loop. The energy of these particles would build and build, flooding the wormhole's throat not with a manageable stream, but with an infinite torrent. This isn't just a radiation bath, it's a cataclysm. The energy density would skyrocket toward infinity, creating conditions so extreme that the fabric of the tunnel itself would be torn apart. The wormhole would be obliterated the instant it became a time machine, collapsing into a singularity or simply dissolving before a single paradoxical event could occur. In this view, Hawking's conjecture paints a universe that is inherently consistent, one that defends the linear flow of cause and effect with ultimate physical force. The dream of visiting yesterday isn't merely technologically out of reach, it's physically forbidden, a door the universe is programmed to weld shut the moment someone tries to turn the handle. Hawking's conjecture suggests a universe that protects its own timeline, but the ultimate verdict on such cosmic architecture lies with a deeper judge. The final word on whether traversable wormholes can exist, even in theory, will come from a complete theory of quantum gravity. This is the holy grail of modern physics, the framework that must unite Einstein's majestic description of curved spacetime with the probabilistic rules of the quantum world. Both are needed to describe the heart of a wormhole. General relativity paints the large-scale tunnel, the warped geometry of the shortcut. But to understand what truly happens in the violently curved, microscopic region of the throat, we need quantum mechanics. It is here, in this zone of extreme conditions, where the fabric of reality is stretched beyond recognition, that the two great pillars of physics clash. Their current descriptions are incompatible, like two brilliant artists trying to paint the same canvas with different sets of rules. Without a unified theory, we are essentially trying to judge the stability of a bridge by only looking at its blueprints and the molecular structure of its steel, but never understanding how they interact under immense stress. The quest for quantum gravity is the quest to write the rulebook for this interaction, to understand how spacetime itself behaves when it is pinched, folded, and probed at the smallest scales. Several profound approaches are vying to become that rulebook. String theory, with its tiny vibrating strings and extra dimensions, might ultimately reveal that the specific configurations of energy needed for a traversable wormhole are impossible to arrange without the entire structure collapsing into a higher dimensional mess. Loop quantum gravity, which proposes spacetime is woven from discrete, finite loops, could show that the smooth throat of a Morris-Thorne wormhole is an illusion, that at the quantum level the tunnel's geometry is granular and chaotic, preventing any coherent passage. The holographic principle, which suggests our three-dimensional reality, is a projection of information stored on a two-dimensional surface, might reinterpret wormholes entirely. In this view, a traversable tunnel could be not a physical gateway, but a specific kind of entanglement between distant bits of cosmic code, a connection that is informational, not geometric in the classical sense. Each of these frameworks could deliver a final mathematical verdict. They might prove that macroscopic, traversable wormholes are strictly forbidden, that the universe's laws contain a hidden clause that permanently outlaws such shortcuts. Or they could show that wormholes are possible, but only in forms we can scarcely imagine, perhaps as ephemeral quantum objects, or as structures that exist for mere instants before decaying. They might even reveal that what we call a wormhole is simply one face of a more fundamental phenomenon, like quantum entanglement, making the dream of flying a ship through it a profound misunderstanding of its true nature. Until that theory is complete, the wormhole remains suspended in a state of quantum uncertainty itself, a ghost in the equations, neither fully possible nor fully impossible, waiting for the final arbiter of reality to speak. While the final theory remains out of reach, we are not left waiting in the dark. A powerful new tool has emerged to explore these cosmic riddles, one that operates not with telescopes but with processors. The frontier of wormhole research has moved decisively into the digital realm, where supercomputers perform symphonies of calculation that no laboratory could ever contain. Researchers in computational physics are now building virtual universes, crafting intricate simulations that marry the vast equations of general relativity with the probabilistic flicker of quantum fields. These are not simple animations, but rigorous digital experiments where every point in a simulated spacetime obeys the precise mathematical laws we believe govern our own. By feeding these systems the initial conditions for a theoretical wormhole, scientists can watch, in accelerated detail, how such a structure would evolve. Does the throat snap shut in a fraction of a nanosecond? Does the exotic matter distribution hold, or does it fragment under its own impossible stress? Does the introduction of even a single particle of simulated matter trigger a cascade of quantum radiation that destroys the tunnel from within? These simulations probe stability in ways pencil and paper math alone cannot, revealing hidden instabilities and unexpected behaviors that guide theorists toward more robust models or away from dead ends. They allow for the testing of formation scenarios that are pure speculation, like the violent collision of cosmic strings in the early universe or the inflationary stretching of a quantum fluctuation. In these virtual cosmos, we can witness, step by step, whether such events could plausibly birth a stable passage or if they invariably produce a chaotic, short-lived knot. This computational approach provides a crucial bridge. It takes the elegant but static blueprints from theorists and breathes dynamic, chaotic life into them, showing how these structures would actually behave in a universe that is never perfectly still. The insights are profound, not because they prove wormholes exist, but because they rigorously test the limits of our own equations, revealing where our understanding of spacetime itself might fracture under the strain of its own logic. These digital laboratories guide us toward the tangible frontiers of research, the unresolved questions that physicists are actively pursuing with pen, paper, and processor. The first and most pressing question is the enigma of exotic matter. Can this substance with negative energy ever be stabilized or even sourced from the quantum fields we already know? The faint whisper of the Casimir effect proves the concept exists, but scaling it up is the challenge. Researchers are exploring whether complex configurations of electromagnetic fields or the strange properties of certain quantum states like the Bose-Einstein condensate could generate and sustain the necessary repulsive effect on a larger scale. The quest is not necessarily to find a new particle, but to learn how to engineer the vacuum of space itself, to coax a persistent, macroscopic region of spacetime to push rather than pull. This leads directly to the second grand question, one for a future theory of quantum gravity. Even if we could assemble exotic matter, do the deeper laws of the universe permit a macroscopic, human-sized tunnel to remain open and traversable? Our current simulations use our best approximations, but the final answer lies in a complete theory that describes the quantum structure of spacetime. Such a theory might reveal a fundamental granularity to reality, a pixelation so fine that any attempt to smooth it into a stable throat is impossible. Alternatively, it could show that the act of traversing itself introduces quantum decoherence, causing the tunnel to collapse the moment classical matter tries to pass through. The question of macroscopic traversability is not just an engineering hurdle. It is a profound probe into whether the universe's quantum rules and its large-scale geometry can ever be reconciled in such an extreme configuration. A parallel line of inquiry asks if we can bypass the exotic matter problem entirely. This drives research into modified theories of gravity, extensions or alternatives to Einstein's general relativity. In these frameworks, like certain brainworld scenarios or theories involving torsion, the equations of spacetime themselves are different. Some of these models suggest that the extra terms in the equations could provide the necessary repulsive geometry intrinsically, without requiring a lining of impossible matter. The wormhole would be a natural, stable solution of the cosmos's own rewritten rules. Finding such a self-supporting solution is a major theoretical pursuit, as it would sidestep the most prohibitive requirement and suggest that the universe might build its own shortcuts after all, under laws we have yet to fully describe. All this theoretical work ultimately points back to the sky. The fourth pivotal question is purely observational: what would constitute an undeniable signature? Researchers are refining the models for gravitational lensing, calculating not just the symmetric light curve, but also the specific polarization patterns of light that has skirted a wormhole's mouth. They are simulating the spectral fingerprints of exotic matter, should it radiate, and the dynamic behavior of an object that might flicker in a way no star or black hole ever could. The goal is to develop a precise multi-messenger profile, a set of predictions so unique that if astronomers see this combination of light, gravity, and perhaps even neutrino patterns from a single point in space, the only reasonable conclusion would be a tunnel in the fabric. Defining that unambiguous signature is what turns speculation into a testable hypothesis, transforming the wormhole from a mathematical idea into a potential discovery waiting in the data stream of the next generation of telescopes. These four questions form the coordinates for the next leg of the journey, mapping the unknown territory between our current understanding and a potential new chapter in the story of the cosmos. The equations on the page point to a cosmos far stranger than the one we see. Beyond the daunting physics of construction lies a quieter, more profound implication. The mere possibility of wormholes, their allowance within the mathematics of gravity, challenges something foundational in our perception of the universe, the idea of absolute separateness. We are accustomed to a reality where 2 points are divided by the empty expanse between them, where influence travels at a finite speed, and where here and there are distinct, isolated conditions. Wormhole theory whispers that this might be an illusion of scale, a limitation of our perspective. It suggests a cosmos where any two locations, no matter how distant, are potentially neighbors. The universe may not be a collection of isolated islands in a sea of void, but a single, multiply-connected fabric where every thread could, in theory, be tied to any other. This redefines locality itself, the principle that objects are only directly influenced by their immediate surroundings. If a tunnel can link my kitchen to a star in Andromeda, then those 2 points share an immediate surroundings through the throat, making them local in a geometric sense, even while being astronomically far apart in ordinary space. The cosmic map is not fixed, it is flexible, and its points are not permanently distant, only apparently so from our limited view. This shakes our understanding of causality, the relationship between cause and effect. In a multiply-connected universe, an event here could become the cause of an effect over there without any signal crossing the intervening space. It simply takes a different, shorter path. The speed of light as the ultimate speed limit for information remains, but it is a limit for travel across the surface of the fabric, not necessarily through its folded layers. This does not break physics, but it profoundly complicates our classical, linear storytelling of how events influence one another across the cosmos. The deeper message is one of potential unity. The fact that Einstein's equations, which so beautifully describe the force that shapes galaxies and guides planets, also contain the blueprints for shortcuts, hints that the laws of physics are not just local rules. They are global architects describing a reality where connection is a fundamental geometric option. This points toward a universe where the laws themselves may be deeply interwoven, where gravity, quantum mechanics, and the structure of spacetime are not separate puzzles, but different expressions of a single, coherent reality whose full shape might be one of breathtaking interconnection. To contemplate a traversable wormhole, then, is not merely to dream of a faster ship. It is to question the very nature of distance and isolation in our universe, and to wonder if the loneliness of the void is not a fact of existence, but a feature of our current understanding, waiting to be folded into a new, more connected whole. This mathematical ghost has guided us through the heart of modern physics. What began as a curious, seemingly impossible solution in Einstein's equations has unfolded into a complex nexus, a single idea touching the deepest mysteries of gravity, quantum weirdness, and cosmic destiny. The traversable wormhole, a doorway to the stars, remains firmly in the realm of theory, shielded by obstacles that seem insurmountable: the need for impossible exotic matter, the threat of quantum fire, and the universe's own apparent defenses against paradox. Yet the true value of this decades-long pursuit was never about booking a ticket to another galaxy. It has been about the journey of understanding itself. By daring to ask if such a tunnel could exist, physicists have been forced to stretch our theories to their breaking points, revealing hidden connections and profound tensions. The wormhole has become a vital thought experiment, a pressure test for our most fundamental ideas about space, time, and information. It forced a dialogue between the vast geometry of general relativity and the spooky connections of quantum entanglement, suggesting they might be two languages describing the same underlying reality. It entangled itself with the fate of information in black holes and the accelerating expansion of the cosmos driven by dark energy. In chasing this phantom tunnel, we have not found a shortcut through space, but we have found countless shortcuts to deeper questions. The pursuit continues not with spacecraft but with equations and supercomputer simulations, illuminating the dark edges of our knowledge. So while we may never step through a cosmic archway, the very act of contemplating it has reshaped our map of reality, reminding us that the universe's greatest secrets are often hidden not in distant stars, but in the elegant, bewildering logic of its own design. What do you think lies beyond this theoretical horizon? Share your thoughts on this enduring cosmic mystery.